So let's start. Hello everyone. Welcome back to another session of India ML Rating Group. And today we have with us Vaibhav Bihani from IIT Delhi. He'll be talking about StriderNet, a graph reinforcement learning approach to optimize atomic structures on rough energy landscape. So Vaibhav is currently a PhD student at Yardi School of Artificial Intelligence at IIT Delhi. He has been very actively involved in the multi-scale multi-physics mechanics research group MTRG at IIT Delhi. His research focuses on the fascinating intersection of material science and AI, with a particular emphasis on graph neural network based modeling and optimization of disordered materials such as glasses, cements, and nanomaterials. He has received several awards, including the Alfred R. Cooper Scholar Award from the American Ceramic Society, O.P. Jindal Engineering Management Award, and Professor K.C. Iyer Graduation Award from IIT Delhi. He's passionate about the ongoing development in his research area. Vaibhav is driven by strong desire to contribute meaningful contribution to society through his scientific endeavor. With this introduction, it's over to you, Vaibhav.
Okay. Thank you. Thank you, Kishle, for the great introduction. And thank you all the participants for joining today. So I'll start with the presentation now. So the title of the presentation is StriderNet, which is a graph reinforcement learning approach to optimize atomic structures on rough energy landscape, which was published in ICML last year, 2023. So going further, so yes. So first question is, why do we need to optimize atomic structures? So the basic reason is that atoms are the building blocks of all the materials, and the structures they form when combined affects the overall behavior of the material, including the mechanical strength, hardness, toughness, and its reactivity, durability, and the thermal properties like conductivity, heat capacity, and there are many more. So if we want to have targeted materials and to have like novel materials to have targeted applications, we need to optimize atomic structures at the atomic scale. So it has various applications. For example, in drug discovery, we want the the drug target to target a particular structure. So to have like this binding affinity, we if we want to control that, we need to optimize its structures and so on and so forth. We have other applications in nanotechnology, in material synthesis for targeted applications, and even when we talk about like carbon capture technologies, it requires these materials which are has to be optimized at the molecular level. And further, like semiconductors, which are used in all the chips in the computer technology, they also need to have these optimized structure. So now what is the problem with these optimization of atomic structures is that the landscape of these atomic structure is very rough. For example, for an atom system, since we have 3 degrees of freedom, it will have three dimensions. So it will be around, if we have 1,000 atom system, it will be around 3,000 and so on. And 1,000 atoms is like very small number. But because of computational challenges, it is like the general thing that people have simulated so far. We can go to up to billions, but that requires much more resources, and we will talk about those challenges in the further slides also. The second problem is it is very rough, so it has very large number of minimas and saddle points. Again, it comes from the high dimensionality, because as the number of dimension increases, the saddle points increase, and there are some theorems that prove it that the rise is kind of exponential. And especially in the disordered system, which I am interested in, like glasses, it is said to be even more rough and more difficult to optimize. And for example, a study in 1993 showed that even a small system or 147 atom can have around 10 to the power 60 distinct minimas. Now, there is a second thing that why we want to study these energy perspective of these materials is because of the aging of materials. So when we want to study the aging of the material, then the energy landscape perspective helps. So, and thermodynamically, since every system tries to attain a lower energy state over time, and we can explain it through jumps from one basin to another. So what happens is, because of the thermal vibrations, the system will try to jump from one basin and it will reach another basin which will have a lower energy, and with time it will kind of reach another stable state, and we can study its properties. But these studies are uh, these studies are important but as well as difficult. So why it is important is because if we want to study, for example, durability analysis for any material that we want to have like a life of 100 or more years or so on, and even in the geological deposits we use glasses and those kind of materials for nuclear waste immobilization, and since they are to be like stored for maybe like a 5,000 year or more period, then studying of these materials for that time scale is more important. But because of we don't have that much time, and even the computational modeling of these materials for aging is very difficult. So we need to develop some kind of accelerated aging methods, and that includes optimization of their structure with time. So that is one of the reasons that we are studying this problem. Then now I want to talk about like when we started this work, what was our motivation behind it. So we were like studying the disordered glasses systems. So this image shows like how the glass is formed. So glass is actually formed by cooling a glass from high temperatures to low temperature. This is kind of pouring the glass in a plate, and as it cools down it will reach to a stable state, a glassy state actually. And one study has shown that the cooling rate affects the final energy of the glass and hence its stability. So if we see these curves, these are for the different cooling rates. So these are actually from the computational modeling of these glasses. And if we see that 10 per minus 3 cooling rate is very high energy, and uh, like 10 to minus 8 is low energy. The Y scale, if you think it is like very small difference, but actually in terms of actual glassy system, this small difference, even this small difference can have large implications on the properties of the material. The another computational challenge in these computational modeling of these glasses is that the simulation time that it takes for let's say tensor minus 3 system is like 1 hour or 2 hour, but as it increases we need even much more time that rises exponentially. For example, this tensor minus 6 might take a month long simulation to just get the structure. So that was the problem. And then we asked ourselves the question that can we reach very low energy configuration by just moving around the atoms and displacing those atoms. So that was the main motivation. And formally stating the problem is basically this: we have a box of atoms on the in the left hand side which is like unoptimized structure. It has high energy, and we want to somehow move the atoms to a lower energy configuration. There are several optimizers that already exist, but they have some limitations that they get stuck in local minima. They don't reach much lower energies that we want to obtain. So then we tried to see whether we can employ a machine learning approach to get ultra stable, low energy, ultra stable classes. So then we came up with this graph reinforcement learning approach. So behind the reinforcement learning approach, the main motivation was that in reinforcement learning, we can explore the energy landscape and try to find low energy minimas and so on. And the motivation behind these modeling of graphs is very simple because atomic systems have these natural graph-like structures, so we can model them as graphs. So then I will now come to the main methodology of the paper. So what we have in the reinforcement learning method is we have two modules basically. One is the agent, the intelligent agent, which has some goal in mind. For example, it wants to optimize the atomic structure from high energy to low energy. And the environment is basically the whole atomic structure environment. And the main thing about the environment is the interaction between the atoms. What kind of interaction happens between the atoms? The agent does not know about that. It only knows like the total energy of the system and some properties, but it doesn't know like how they are interacting. So it needs to interact with the environment to know whether displacing these atoms in one direction is better or other direction is better. So this is the main formulation. Now I will go into deeper into how this reinforcement learning is formulated in this context. So first we have the environment. In the environment, we have graph-based representation of the atomic structure in which we model the atoms as the nodes and the bonds between those atoms as the edges. And we have the agent, which is basically a neural network, and it's called a policy pi because it predicts the actions, and it is parameterized by some parameters theta, and it can take small actions like which is defined like 80, the small displacement for the atoms in three-dimensional space. And at each action that it will take, it will receive some reward from the environment, and we define the reward to be reduction in energy. So the reward will be positive if the action leads to a lower energy state, and it will be a negative reward or a penalty if it increases the energy. And the learning algorithm that we will be using is policy gradient learning. So in policy gradient learning, we have the objective, which is on the right side that I am showing. So the objective is basically the sum of the rewards that the agent will get on in acting in the environment for T steps. The expected value of that reward, that that expectation will definitely depend on the policy, because policy is the one that is giving the actions, and that policy, since it is parameterized by these theta parameters, each of the action will affect what trajectory it will be following. So this expectation is over the trajectories that will be sampled if we have some policy with some parameters theta. So for example, we have some fixed parameters theta, and if I take some action, I will have this trajectory, or if I take some other action, I will have this trajectory. And the goal of the reinforcement learning, this reinforced learning, the policy gradient learning algorithm, is to increase the probability of those trajectories which will lead to higher rewards and reject those trajectories that will lead to a lower reward. So this is basically then argmax over these theta parameters. These theta parameters this controls the probability of the actions, and it tries to move that distributions toward higher reward trajectories. And I will not go into the details of this algorithm right now, but basically what we have, this loss function in conventional ML, we have similar cost function in RL, and this can be just optimized similar to any other networks using this policy gradient, which is defined in the below equation. And it has basically two components. The first component, it's the discounted rewards dt, and minus a baseline. So baseline, I will talk about it in further slide also, but it is there to reduce the variance in the reward signal, because since we don't have the actual label, the rewards that we'll be getting will not be like a true reward, it will have very high variance. So that is the problem. And the second term is the pi theta, is basically the probability of action taken at time t given a state of the graph at time t. And we basically take the log of that. It comes from the derivation of policy gradient and the gradient of that, and we optimize our theta parameters based on the gradient of this objective function. Now I will come to the modeling of environment as atomic graph. So the atoms are like point cloud that are embedded in 3D space, and they're interacting with each other. So we want to somehow encode that information of the environment into some representation. And for getting that representation, we are using graph neural networks. And in graph neural network, we have some feature representation for each node and each edge. Just like in conventional CNNs, we have some representation for pixels. And there in CNNs, we have this kernel function. Similar to that, we have in graphs, we have two operations. First is the message passing, and second is the aggregation. Message passing is like this kernel operation in CNNs only. We have some cutoff radius for the neighborhood, and all those atoms within the neighborhood, though their feature representations will be concatenated and passed to the central node in, and its feature representation will then be updated using that features of its neighborhood. And if we increase the layers of the message passing, then we will get information from the further far nodes, like the second neighbors, the third neighbors, and so on. So this Mij is basically the message that the jth node gives to the ith node. J is the neighborhood node, and I is the node that we are considering for this example. And its representation is updated based on its own representation and the aggregated representations from its neighborhood. So these are two main steps, and the goal is finally to get a neighborhood representation for each node and each edge, so that each node has a information about its neighborhood structure and the environment, so that it will know like moving these atoms should be good or bad based on these embeddings. And there are actually many architectures that models these atomic systems. There are several studies. You can look at this article which talks about the recent GNN architectures for 3D atomic systems. Then now I'm coming to the exact architectural details of the model. So stepwise we will go like what are the steps that we are following. So the first step is to define the system. So we have atomic system, we have all the coordinates of the system, and based on those coordinates, and we have from the environment, we have an energy function that can calculate the energy of the system, and also the pairwise energy of this of between any two atoms. So we can define some features for the node and for the edges. For the node, we give the feature, the first feature is the atom type. For example, it can be carbon, hydrogen, or what atom it is. The one hot encoding of that representation is the atom type. Then the potential energy of the atom, based on the energy calculated, we can have the energy of each atom that is also given as a feature, and correspondingly the mean interaction energy in the neighborhood that can also be given as a feature. Then for the edge features, we give a 3D edge vector. The between any two atoms, we can define the edge vector dx, dy, and dz. Then the second feature is the equilibrium bond distance sigma minus the actual length. So this is actually an important feature, and we see that it really affects the performance also. So what I mean with by the equilibrium bond distance is that if you have only two atoms in an isolated environment, what will be the equilibrium distance that they will have? Because we can minimize that energy function and get the equilibrium bond distance, and it's act like a constant between any two fixed types of atom. And the actual length in the actual molecule or the structure will be either kind of stretched or compressed from the equilibrium distance. So this kind of gives
So there is a
the.
question, I think. Yeah, Simon has a question. Simon, you can ask.
Yes, yes, sure.
Yeah, we can't hear you, Simon. Um, no, I think we can't hear him. So maybe you can type it in the chat so that we can take it. Yeah, I think you can continue.
But I have one question. Can I ask now
Okay.
or should I
Yeah,
wait
yeah,
till end?
yeah, yeah.
So actually
Maybe.
it's regarding the basic problem foundation itself. So as you said, like you're looking for the optimal arrangement of atoms inside it, so to minimize the energy as much as possible.
Right, right.
So like you get that, okay, you did some like as you're talking about that simulation, so
Mm,
you get then some structure. Okay, there's a structure which should be which should give us the lowest possible energy. So do you
mm.
literally go to that part like in reality and change the atomic level positions and all? Like I'm not able to imagine that. Like does it happen?
You, do you mean like experimentally? No, because these are all computational modeling of those materials. But even in those, we can have some signatures of the properties that are that can be verified experimentally, but not directly.
So this whatever optimized arrangement you are getting out of it, like that is for theoretically. Because that's what my understanding is. Like as of now, we don't have this technology yet where we can interact
Yes.
at the atomic level and change the position.
Yes, yes. So these are all computational studies. So we can maybe not directly create those low energy structures once we get those, but we can study their properties, and maybe from those properties we can somehow figure out what are the ways that we can experiment. So that is like a long way forward. But at this moment, it's currently not really possible, as you said.
Okay.
Okay, so we have another question, or I can move?
Oh no, you can continue.
Okay, so now we are at the first step. So we have defined the node features and edge features. Now we will define based on a cutoff, we will create a graph of that atomic system and define the edges and the nodes, and just transform the node features given in the first step to some high dimensional feature representation in the first step. Then we will apply our graph neural network, which will have basically two steps. First step will be the updation of node representation. So the first equation shows how the node representation is updated. So if we have a node V and we have some neighborhood node U, then we will have the feature representation of U node and the feature representation of the edges VU, and we then concatenate those and just apply a linear transformation and concatenates that as well with another its own embedding, and then pass it to another linear MLP, and then apply some activation function that will update our node representation. And similarly, for the edge, for any edge UV, we will have the node representation of the nodes connecting that edge, the HV and HU, and the embedding of that particular edge, HVU. Then we will first pass it through a linear layer and then concatenate the edge embedding and again pass through a linear MLP and get some activation. And we repeat it this step for, let's say, 2 or 3 times, which is kind of a hyperparameter of the model. And then doing so, we will finally get some embeddings for each node that will have the information about the structure. Then we want to predict the action. So in the final layer, what we do is we pass all these embeddings through a simple neural network. The HIL is the embeddings we get at the final layer of graph neural network. And we parameterize the action. The action, since it is a continuous action in 3D space, we to parameterize that we use a multivariate Gaussian in which the mean is predicted from the parameters of the policy theta. Theta is actually all the parameters of this neural network as well as all the parameters that are there in the graph update steps and initial transformation. All those parameters theta that defines the mean of that particular action, the displacement at each node, and the standard deviation is kept as a hyperparameter, which we can also learn, but it is very difficult to learn. It leads to some instabilities in learning. So for this architecture, we have kept it constant, and the mean is a function of the policy parameter. So the mean displacement that the model will predict, it will have some 3D uh, displacement that we will sample from this multivariate Gaussian and then apply those, and we will have some updated graph structure, and then we can do this step for our trajectory of t iterations, and we will finally get some another structure, and we will calculate what is the energy of that structure, compare it with the initial one, and get the reward whether it has increased or decreased. Based on that, it will be given a positive or negative reward. So then we will, based on these theta parameters, we will sample all these trajectories for, let's say, 10 or 20 trajectories and calculate what is the average reward that it is getting at each uh, at these parameters, and that defines our objective function j pi theta that I already defined in the last slide. Then again, we will calculate these policy gradient. And as I mentioned, that the baseline is the one that is very important here. So the baseline that we use in the network is some kind of an optimizer. that also takes the configuration and optimizes it. So it gives the model an idea about that my performance on this graph is this much, and like, can you match this performance? So it will kind of a competitive reward that it needs to it will be given a positive reward if it beats the baseline performance, and the negative if it doesn't. So it has some guarantees about the variance reduction for this algorithm, as well as we can have some comparison with whatever baseline we want to use. So let me now define what the systems that we have studied. So first one is a simple binary Lennard-Jones glass. So it is a well-studied system in computational physics, which is a well-known glass former, and it has a very simple pairwise interaction defined by this equation, which just depends on the distance between two atoms and some sigma and epsilon parameters. And the next system is a similar system, but it has some more parameters, and it is also a pairwise, but depending on the parameters we can adjust the potential well, and we can have some narrow potential well system which are even more difficult to optimize. Then the third system that we considered is Stillinger-Weber silicon. So silicon is like used in the semiconductor chip manufacturing and all, and modeling that is difficult because it has some angular term. So here the energy depends on pairwise interaction, as well as the three body interaction that depends on the distances between three pairs of atoms. So it has another complex term that is kind of difficult to model and optimize. So these were the three systems. And once we train the system, what we see is the plots of the discounted rewards with the training epochs. And since I explained like this baseline, if we are beating the baseline, then we should be able to get positive rewards. So the zero line denotes the baseline performance. So if we are beating those baselines, then we are getting positive rewards. So we see that for all the three systems, once trained, we are getting some positive reward. That means it is performing much better than the baselines. So these were the baselines that were used. One was a simple gradient descent, which follows the gradient path of the optimization because we have the energy function. So we can take its gradient and directly follow the gradient, but it has this problem of getting stuck in local minima, and also the learning rate is constant and cannot be adjusted. Then Adam is a well-known optimizer in machine learning that we always are using. Though Adam has this adaptation of the step size and the direction from the memory of these first and second movements of the gradient, and it is very popular as we know in machine learning application. Then the third optimizer is the FIRE optimizer. It stands for Fast Inertial Relaxation Engine. So it is a molecular dynamics based optimizer. It is also available in many standard softwares like LAMPS and all. And the interesting part is that Fire and Atom, they're theoretically kind of similar. Like their steps are different, but basic idea is similar. So it has this updates of the velocity of the atoms in the simulation, which kind of is similar to the memory of movements in Atom. So they are similar, but still Fire is more popular in molecular dynamics for this molecular simulation. So these were the three baselines that we compared. Then comes the inference part. So in inference, we faced one problem, which is called the long horizon problem. So since we have trained the model for fixed length trajectories, for example, we have trained for 20 steps of trajectory, but in inference, we have to optimize it for many much larger trajectory length. For example, around 1,000 steps are needed to optimize. So this becomes a bit tricky because we cannot directly optimize train the model because of this long horizon problem. Because if we have a long trajectories, then getting the signal from like what action was the one in the trajectory that leads to the final goal, it becomes difficult to assign that credit for each action. So it becomes difficult to train. That is kind of studied in RL also. So what we find is that one solution that we found is that we can adapt the model also during the inference, so that in during inference the parameters of the policy are also getting updated, based on the rewards that is it is eventually getting in the trajectory. So it leads to much higher performance of these optimizer that we have seen, and it allows the policy to adapt to the unseen low energies environment that it has not even seen during training. And it also allows to successfully get more stable configurations. So now I'll show you the results now. So first is the performance that we have observed on different systems. So we considered three systems and three different optimizers. The green curve is our model, and the other optimizers, and we study what is the mean performance. So we see that over the all three models, we have achieved better performance than other optimizers. For the silicon one, we can see that somehow it is performing better, but still it has some like not as good performance as other two systems, and it can be attributed to the three body interaction that we see in the system, which makes it difficult for these models to learn and optimize these structures. So these are the same result only in the tabular form. So we tested it on 10 different structures and calculated what is the minimum energy that we are reaching and the mean energy that we are reaching. And we see that the model performs very good in all three systems and all three optimizers. Then we also did some experiments for the inductivity to unseen sizes, like how well it performs it if we increase the size of the graph. So we see that we had trained the model for 100 atom system, and we tested it for up to 1000 atoms. So for 1000 atoms, the performance is not really outperforming the other ones, but still comparable. Then we did some feature ablation studies. So first we tried to see what other architectures that could have been used for these modeling. So first in the graph we have the training epochs, and on the y-axis we have average reduction in energy in 20 steps. So what we see is that the simple MLP, multiple layer perceptron, is not even able to get to lower energy. It's not even training. Uh, we kind of attribute it because to the problem that in MLPs we cannot directly give the edge information, and it doesn't have those graph interactions that are present in graph neural networks. So because of that, I we believe that it is not able to even get trained to optimize. Then we see that other architectures like full graph network and graph attention networks, they have a good performance comparatively, but the StriderNet one is since better than all the three. And since simple MLP was not able to reduce energy, we kind of conclude that graph structure is very important in these optimization. And then we have this final study of the feature ablations, in which we try to see which are the features that are very important for the model. So what we did is that we removed one feature at a time and study what is the performance gain or performance loss that happens due to removal of that feature. And we see that the red and pink curve are actually the two edge features, and not having any one of the two will actually lead to a very poor performance. So we have seen that the edge features are much more important, whereas the node features, which were basically the potential energy of that atom, the neighborhood potential energy, are important. It enhances the performance, but even without that, without them, the performance is good. So that was the inference that we get from this study. So now I will list out the key takeaways from the work. So we have introduced a general architecture for RL-based optimization for atomic structures with graph-based representation, and shown that it outperforms classical optimizers in achieving lower energies. And also the model adaptation by fine-tuning the parameters along with the inference, it leads to improved performance, is what we have seen. And that the feature ablation studies, that edge information is highly important in this kind of studies of optimization of atomic structures. So that was all for the presentation, and these are all the co-authors and my supervisor. Professor Anoop Krishnan, Professor Sayan Ranu, his PhD student Sahil Manchanda, and Professor Srikanth Sastry. They all help me throughout this project. And this work is the whole code is available on the GitHub. And I also want to acknowledge the HPC facility at IIT Delhi, where all these models were trained. So thank you all. And if you have any questions, I would be happy to answer.
Okay, thank you, Vaibhav, for this nice talk. So there is a question in Q&A which Simon has asked. So I will take this question. So he's asking, how do you create the graph? Since physical bonds are not present in materials like
Hmm.
covalent bonds, and you say
Hmm.
that you use bonds as edges in the graph. So his question is,
Right.
are these graphs multi-graphs? In crystal, graphs are typically constructed using some approximation algorithm like k nearest neighbor, which leads to form a multi-graph. So basically, how the graph is formed, he's asking.
Okay, okay. Yeah, it's a good question. So it depends on the what systems we are studying. So these are all disordered systems. So in these systems, we have a distance-based cutoff. So we decide a cutoff distance in the 3D space, for example, 10 angstrom or something. And whatever atoms are within that 10 angstrom radius, they are all connected with the edges. So that is how the edges are created.
Okay.
I hope that answers the question.
Yeah. I also have a follow-up question of Simon's question. So can you have kind of 3D structure, I mean 3D convolution neural network? I mean, can we take the 3D structure itself and then apply 3D GNN in place of converting into a 2D graph and then applying 2D GNN?
Okay, that is actually interesting idea, but I think it should
Because
definitely work.
yeah, because the recent paper you have just referred there, right? The
Hmm,
manual of 3D GNNs on atoms. So in that
hmm,
paper, I have seen there are many 3D GNN architecture applied on 3D structure.
hmm, hmm, hmm.
So that I was thinking if we can apply those things.
So here also the GNN is 3D. Actually, it's not like the dimensionality of GNN as such is not really the thing because the atoms are in the 3D space and
Hmm.
all the graphs and the distances, the edge features are all 3D.
Okay.
Uh, yes.
Okay. Is
So
there any other question from anyone from the audience?
Yeah, I have a couple of general questions. So may I ask?
Yeah, you can.
Yeah. So first of all, I would like to ask you, like, if you have any of these optimization problems, like as in your case, the atomic structure. So first
mhm,
of all, like how, like I think I missed in your presentation, like how do we convert that into a typical ML problem? Because if we look at the ML side,
mhm,
it's either majority it's classification or regression, so it doesn't directly
mhm.
fits into any of that.
Yes, so this problem is basically we have an energy function, which is a function of the positions of the atoms. So basically, let's say we have 100 atoms with three coordinates. So we'll have 300 parameters of the positions in 3D space, and these atoms are placed in a box, and we have to find such coordinates that minimizes this energy configuration. So that is the main problem.
Okay, so and there should be some equation or some formula where you put these values and then you
Yes,
get the real value. So
yes.
that's what I was
So.
asking. Like, if you convert, if you look from the other class, for the classification point of view or regression point of view, it doesn't directly fits in because, like, there it's basically predictors whether where I will put the input and I will expect the model to give the energy in this case. But
Mhm.
that won't fulfill like the or give the solution for this problem where I want the input which should give the minimum value.
Right. So, yes, right. You are right. So, it is called a combinatorial optimization problem, which we have like a oracle function of the energy. We can just give it the solution, one trial solution, like the configuration, any random configuration, and it will tell us what is the energy. But getting the lowest input, the as you said, the input, the configuration input that will lead to a lower energy is the optimization problem. So even in some cases that evaluating that energy function is also difficult. So in this study, we have taken very simple system. As shown in this slide, we have already the analytical solution, or sorry, not solutions, the analytical equation to evaluate the energy. So once we have all this atomic coordinates, we can define what is the distance between each pair, the R value, and it will give the pair energy for each pair of atom, and we can add all the pairs in the system and we'll get the total energy. So that is how it is calculated, and we have to find such configuration where the coordinates leads to those configuration where this energy is minimized. So yes, it directly does not fit into any regression kind of framework or classification. It is a real an optimization problem that we are solving.
So apart from RL, is there any other viable option which one can think of?
Yes, so interestingly, there is one class called learned optimizers that were like proposed by Google. So they also, what they do is that they have a set of optimization tasks and they train their simple, not graph network, only a simple neural network, and in which they will pass these configurations and get the updated configuration like input positions, output positions, and that should lead to low energy structure, and that is not RL based. That is simple neural network optimization for a large range of optimization tasks. So that also kind of has a very good performance on these atomic system. So that paper is called Learn to Hop. You can maybe have a look at it. So it is it does not use RL, but it has this kind of a learned optimization. So here also we are kind of learning to optimize. So we have some optimizer and we are trying to learn that optimizer, and in their approach they are also learning an optimizer, but kind of differently, not in an RL fashion.
Okay, so that last question, like if suppose I get a, because that's what I was, that's why I wanted to ask you all these questions. Like if I get any optimization problem, then what should be my first approach to solve it? Because I can't directly apply this classification or regression kind of thing. So should I go for RL thing, try to put there, or is there something else which one should try first and then you elaborate on top of it or something like that?
So that definitely it depends on the system. For the 3D atomic systems, so there are basically three categories of these optimizer. One is what I showed, that are classical optimizers like atom, fire, and gradient descent. And these are called classical optimizer and also called local optimizers because they optimize only locally. And then there is the second class called these genetic algorithm, like evolutionary approaches. So they have kind of genetic approach in which they have a set of configurations and evolve them to get a better solution. So that is also second approach. And third is the this learned optimization. So learned optimizer is used in the cases in which you want to kind of have a target system in place and you want to achieve only the low energy configuration in the target system. So once you train on that system, it will perform very well on that system. So for those kind of applications, it is very good. And if you want kind of a general purpose optimizer, then in general these atom and fire that will work for most of the system. They may not give you the very low energy state, but they will at least help you in that the task of optimization.
Thank you.
Okay, any further question? Okay, so I have one last question, Vaibhav. So can you go back to that slide where there's the initial structure and the final structure?
Right?
Yeah. So
Yes, this one.
yeah. So my question is when this materials has this kind of initial structure. When like we have different generating models like CDVA and all who are
Mm-hmm.
generating new material. So are
Mm-hmm.
they generating this initial structure or the optimized structure? That is my basic question.
Okay. Model, so it can also generate optimized structure directly, but in general what I have seen in those CDVA and diffusion models also,
Hmm.
that the structures that is they get is generally have not optimized. So they what they
Okay.
generally do is that generate a structure and use a simple optimizer like gradient descent or some other.
Okay. And then they get this optimized structure, right?
Yes, yes, yes.
Okay. Okay then. Thank you, Vaibhav, for this wonderful talk, and let's thank him again. And yeah,
Thank you
thank
for
you all
attending
for
this.
join. Yeah, thank you all for joining the reading group. Okay, we'll meet again in the next week. Thanks a lot.
Okay, thank you everyone.